Good afternoon, students. Let us review class exercise 1 of topic 19, nitrogen compounds. Okay, so the bulk of this topic is on the property of the nitrogen compounds, particularly those bonded to LQ based functional groups. So broadly speaking, you are getting either amines or amides. Okay, and if you take a look at question 1a, you are given 3 types of amines: methylamine, that is primary; dimethylamine, secondary; trimethylamine, tertiary. Okay, so I'm just going to draw them out. Okay, so methylamine will be CH3NH2, so lone pair of electrons over here. Dimethylamine, I'm just going to draw a NH, okay, and then 2 of this. Okay, so maybe I shouldn't draw the H there. Maybe like this, like this, like this. Okay, and then lone pairs of electrons. Trimethylamine, lone pairs of electrons over here. 1, 2, 3. Okay, so I'm going to highlight the electron donating group. So we have a LQ group, which is methyl. 1 methyl here, 2 methyl here. 2 electron donating groups. 3 methyl electron donating groups for trimethylamine. So question is, describe and explain the relative basicities of methylamine, dimethylamine, and trimethylamine in the gas phase. So the focus is in the gas phase. That means they are not solvated. Yeah, so because of that, it's relatively straightforward. So the focus will now be on the electron donating nature of the LQ groups. Yeah, so the focus of answer will be electron donating methyl groups. Okay, so you focus on this and how it enhances, okay, the electron density of the lone pair of electrons around the nitrogen center. Okay, so for methylamine, there is 1 donating methyl group, dimethylamine 2, trimethylamine 3. So the more electron donating methyl groups I have, okay, it will enhances the availability of the lone pairs of electrons on the nitrogen, or it will increase the density of the lone pairs of electrons on the nitrogen. And when the electron densities of the lone pairs of electrons on nitrogen is enhanced, they become more available to donate to either a H plus or a Lewis acidic site. Yeah, because the focus here is basicity, so we are looking at its role as a base. That means attracting a H plus. Okay, so attracting H plus. Yeah, you can also look at it as how much it's willing to be attracted to a Lewis acidic site. Yeah, because basicity here is not defined. Are we looking at Lewis base or are we looking at Bronsted base? Yeah, so you can answer the question from both perspectives or one of the 2 perspectives. Yeah, but it doesn't change the answer, because the idea here is the more electron donating groups you have bonded to the nitrogen, the more available will the electron densities around the lone pairs of electrons on nitrogen be. So the greater electron densities, the more they will be attracted to H plus, or the more they will be attracted to Lewis acidic sites. Okay, so with that, I think 1A will be relatively straightforward, quite easy to answer the question according to what the question wants. So it's a 3-mark question. There are 3 unknowns here. Of course, in that case, it will be easy to tackle them. Okay, we're going to move on to B part 1. Okay, so the Kb values of 4 bases at 25 degrees C are shown. Okay, so this is Kb, not pKb. So remember, the bigger the Kb, the greater the extent of ionization. Okay, yeah. Then we have ammonia. So usually we will use that as the benchmark. Okay, so ammonia with the benchmark, I'm going to highlight in yellow. Okay, so that's 1.8 times 10 to the power of minus 5. And then we have ethylamine. So you notice that for ethylamine, right, it is about 10 times, okay, so maybe about 20-ish times more basic than ammonia. And we can easily understand this due to the fact that it has an electron donating ethyl group. So the argument will be the same as 1A. Yeah, so compared to ammonia, ethylamine has one electron donating ethyl group, which enhances the electron densities around the lone pair of electrons on the nitrogen. Okay, so that makes it more susceptible to ionize, or more susceptible to attract a proton from H2O. Okay, so you're supposed to write the Kb expression. So maybe I'll write the Kb expression first. Okay, so in this case, Kb is equals to, you're supposed to write for ethylamine. Okay, so that will be the conjugate acids, which is NH3 plus, okay, and then OH minus, and then divide by the concentration of ethylamine. Okay, yeah, and then the question asks you to explain the relative magnitudes of the Kb values in the table. Okay, so I'm just going to explain over here, just using the table alone. Okay, so I've explained why ethylamine is more basic than ammonia. Okay, so I will not repeat myself. Next, we look at phenolamin. Okay, so for phenolamin, the explanation will be similar to what we discussed for phenol. Again, how the lone pairs of electrons on nitrogen can partially delocalize into the phenol ring. Okay, so I'm just going to draw the p orbitals of the carbon in the phenol ring, and then I'm just going to draw out nitrogen, and then projecting out, projecting in. Okay, the lone pairs here. Okay, so there's no orbital mismatch, although I drew it. It seems that I drew it a bit bigger, but carbon and nitrogen are all in period 2. So, okay, so the electrons, the lone pairs of electrons can partially delocalize into the phenol ring. Why did I use the word partially delocalize? So I'm just going to emphasize it. Partially delocalize. Okay, I use the word partially delocalize is because nitrogen is more electronegative than carbon. So I would not expect the delocalization to happen to the same extent as that in an amides. So I think partially is important here to emphasize that fact. Another common question students ask is, based on chemical bonding, the nitrogen has 4 electron domains or electron groups, 3 bond pair, 1 lone pair. Why is it that it takes on a trigonal planar geometry instead of a trigonal pyramidal geometry? Okay, so I can explain that as well. In fact, it may have already been explained under the topic of chemical bonding, but I'm just going to explain it again over here. Okay, if it's going to take on the trigonal pyramidal geometry, you will notice that the lone pairs of electrons will be something like this, and it will be slanted. So the delocalization or the partial delocalization of the lone pairs of electrons into the phenol ring will not occur appreciably, or will not occur as good as that when it's sp2 hybridized. Okay, or when the lone pairs of electrons is found in the p orbital. So no matter how you argue, whether you say that lone pair of electrons is in the p orbital versus sp3, or you want to say that the nitrogen is sp2, so therefore the lone pair is in the p orbital, and for the case of the one below, then everything is sp3 hybridized, so lone pair of electrons is sp3. No matter how you phrase your answer, you are actually talking about the same thing. The fact that if the lone pairs of electrons is found in the sp3 hybrid orbitals, its partial overlap with the p orbitals in the phenol ring will not be as good as that when the lone pairs of electrons is found in the p orbital. Yeah, so because of that, you will notice that when a heteroatom is bonded to a pi system, it will tend to its geometry will tend to try to fit itself into a geometry where its electron density can be effectively delocalized into the pi system. And that electron density could mean a lone pair of electrons, it could mean a radical, or it could mean that its p orbital is empty and electron density from the phenol ring or from the pi system needs to partially delocalize with it in order to spread out the positive charge. Yeah, so if you have that idea in mind, then it's actually relatively straightforward to discuss and to understand why, in this case, phenolamine, right, has a much lower Kb as compared to ammonia and ethylamine. In fact, it is like 100,000 times less basic. If you look at the value, it's in the magnitude of 10 to the power minus 10. Okay, and then now maybe we'll compare between phenolamine and 4-chlorophenolamin. Okay, so for 4-chlorophenolamin, right, there is an extra group here, substituent group, is chlorine. So chlorine, as we all know, it is inductively withdrawing because chlorine is more electronegative than carbon. And because it is inductively withdrawing, its withdrawing nature through the sigma bonding framework will further cause the electron density at the lone pairs of electrons on nitrogen, right, to be reduced. Yeah, and because of that, the lone pairs of electrons on nitrogen for 4-chlorophenolamine, its electron density is less than that in phenolamine, and because it's less than that in phenolamine, its extent of ionization will be lower than that of phenolamine. Okay, so once you have that in your explanation, then I think everything else is straightforward. You'll be able to understand why 4-chlorophenolamine is less basic as compared to phenolamine. Okay, and why phenolamine is less basic as compared to ammonia. I think we have discussed it. Yeah, so normally when we discuss this, suggestion on how you should phrase your answer would be what I've discussed earlier on. So I won't go into details, but I would suggest that first you compare 2 with 1, okay, because 1 is usually the benchmark because the nitrogen is not bonded to donating or withdrawing groups. Yeah, so it's easier to discuss. So you discuss 2 with 1, and then after that you discuss 3 against 1, so that you are able to establish the fact that phenolamine is less basic than ammonia, and ethylamine is more basic than ammonia. Yeah, and then after you are done with that, then you can discuss 3 versus 4, and that will complete your explanation. Okay, yeah. Then so we are done with this. Then of course finally explain why amides are neutral rather than basic. Okay, so amides depends on how you want to discuss. For amides, the lone pairs of electrons is effectively delocalized across the CO pi framework. Okay, so if you do H3, you can easily draw this particular resonance structures if you wish to. For a more H2-ish kind of answers, you don't need this, but I thought I'd just show you this first. So this is how you show delocalization, or how you represent delocalization using resonance structures. Yeah, if not, you can easily show the orbital overlap diagram, something like this. So I'm just going to show it like this. Okay, CO pi system, we have R here, and then we have N, okay, H, and then with a lone pairs of electrons like this. Okay, so over here we can show that these lone pairs of electrons delocalize across the CO pi system like this. Yeah, and this delocalization will happen to a greater extent as compared to the NH2 in phenolamine, because I think you have to emphasize this, because oxygen is more electronegative than nitrogen. So that is the reason why the delocalization happened to a much greater extent as compared to that in phenolamine. Okay, then let us move on to question 2, part 1. Explain how the basicity of benzolamine will be compared to that with ethylamine. Okay, yeah, so some of us might be tempted to say that for benzolamine, right, the lone pairs delocalize into the phenyl ring. That is wrong, because there is a CH2 over here. Yeah, okay, so what you want to discuss is probably look at the extent of ionization. Okay, so let's look at how this is ionized, CH2 and H3 plus. Okay, and of course for ethylamine, we are looking at the same thing, equilibrate to give me NH3 plus plus OH minus. Okay, plus OH minus. So let us focus on how effectively are the conjugate bases being solvated. Okay, why is that the case? Because both are primary amine. Yeah, and to decide on how much or the extent of ionization, right, one other factor is we should look at solvation. How effectively are the conjugate acids being solvated? Yeah, so you will realize that for the conjugate acid of benzolamine, right, it has a much larger benzyl group. Okay, which might interfere in the formation of the ion dipole interaction the conjugate acid forms with water molecules. Yeah, so because of that, right, the extent of ionization of benzolamine will not be as great as that in ethylamine, because the conjugate acid of benzolamine is not as effectively solvated as the conjugate acid of ethylamine. Yeah, so because of that, because the extent of ionization is not as great, then I would expect benzylamine, right, to be a weaker base as compared to that of ethylamine. Yeah. Another way, another explanation that some of us would like to give is related to hyperconjugation, but the explanation using hyperconjugation is not that straightforward, because hyperconjugation is not exactly in the H2 curriculum. Yeah, how do we explain hyperconjugation? If for those of us who are interested, so we know that alkyl groups are electron donating due to an effect known as hyperconjugation, due to the CH sigma bond that partially overlap with whatever electron densities we are looking at. So in this case, right, you notice that there is a CH2 group next to the phenol ring. Okay, the CH2 group enhances the electron density of the phenol ring due to hyperconjugation, but it also enhances the electron density of the amino group. In the electron density of the amino group. Yeah, so in this case, you notice that the CH2 is stuck in between the two. Yeah, so its effectiveness in allowing the enhancement of the electron density is now spread out between the phenol ring and the amino. Yeah, but for the case of ethylamine, right, the CH2 is essentially just having its effect largely on enhancing the electron density of the lone pairs. Yeah, so with that idea in mind, ethylamine is therefore a stronger base as compared to benzylamine. Yeah, so that is an explanation you can give if you are familiar with the concept of hyperconjugation, but it's not a very straightforward thing to explain, especially if you are not comfortable with talking about that. Okay, so I'll rather you stick with the extent of ionization as a key explanation. Okay, then the last part, question 2, part 2. Suggest why bromine water could be used to distinguish between 4-methylphenollamine and benzylamine. Okay, so basically for 4-methylphenollamine, right, bromine water is able to undergo electrophilic substitution effortlessly. Okay, then state any observation. Okay, so yellow-orange aqueous bromine will decolorized. Okay, then you might observe white PPT, or you might not observe white PPT of the resulting product. So we are not very sure because you have to do an experiment to figure out. Okay, but all we know is, okay, so bromine aqueous. Okay, so we don't need to write aqueous. Okay, and then we are going to expect the bromine to be substituted at the 2nd and 6th position, and then with the production of HBr. Of course, HBr in aqueous medium will be simply H plus and Br minus. Yeah, but you must be very clear that you need a 2 here. Yeah, because some of the students just put Br2, and then after that over here they put hydrogen gas, but this is not possible. Yeah, because this H here has an oxidation number of +1, so it will come out as a H plus rather than it gets reduced to hydrogen gas. Yeah, so this is the most common mistakes that students will make in a question like this, thinking that hydrogen gas will be evolved. Yeah, so remember that in the process of electrophilic substitution, the H is released into the system as a H plus, not hydrogen gas. Okay, so with that, we have come to the end of the review to class exercise 1.